2.45 times 10 to the 8th miles, and the distance between the foci is 3.08 times 10 to the 6th miles. Do you have an equation for eccentricity?
Let me see.
I have one that I'm trying to find that I really like, and it's something over something, but let me try to find it here so I can help. There it is. So eccentricity is C over A. That's not helpful. Okay. All right. I'm sure it's the ratio of one of these to the other, or maybe half the other, but I do need to look, unless you know.
It's distance between foci over length of major axis.
Say that one more time. I didn't quite catch all that.
It's distance between foci
Over the major axis.
It's distance between foci over length of major axis. Yes.
Okay. So it's essentially it's this number. I'm sorry. So this is the foci and then the major axis. So sorry, it's the 3.08 times 10 to the 6th over 2.45 times 10 to the 8th.
Mm-hmm.
So let me get my calculator out. If you've got one, I encourage you to use it. You can use the E if you need to. 3 times 10 to the 6th divided by 2.45 times 10 to the 8th. So I get 0.0126. And notice the units are the same. So they just cancel out miles over miles. So it's just this number here. But go ahead and check that, make sure it's something you got.
Yeah, that's what I got.
Right. Okay, so now we can move on to question number 2, which is something about orbital period. Let me just grab this question. How do you feel about your work on this problem so far?
I kind of started it. I'm not too sure if it's correct.
It looks pretty correct to me. I usually see as P equals D to the 3/2 power, but let me just check. This is not my area of expertise. These. Let's see if I can find one. Yeah, so you have it here. It's P squared, which is the period in years, equals A cubed, or D cubed is fine. The problem is that it says A is the semi-major axis, which is probably okay. Like I doubt your instructor's making this super complicated, but if you were to like you did here, if you were to take the square root of both sides, P is equal to A to the 3/2 power, because the square root equals X to the 1/2. So it's just this power, this number here is 6.58 times 10 to the 11th to the 3/2 power.
That's always the type calculator.
There's a lot of like interference in your communication. If I'm having issues, let me know. Also, I'm having trouble understanding you.
Is that better?
Yes.
Okay. So is that all you have to put in your calculator? Is the 6.5?
Yes.
Oh, okay.
Yeah, 6.58 times 10 to the 11th to the 3/2 power. This is like a plug and chug type problem where you get a number, and then or the numbers, and you just put them into your calculator.
And you don't have to convert anything?
No, as far as I know.
Okay.
There are other equations that require you to know like the mass of this and periods and stuff like that, but I don't think your instructor gave you one number here. I think it was just like, hey, here's the formula. Let's see if you can use it.
Okay.
Calculate the distance between the planet and the sun if it has an orbital period of 6.47 Earth years. See, I see you converting things here, and that's what bothers me about what you did, about what we just did. So
Yeah.
let me double check here. I'm definitely not like, as a little tired. So let me just check here. Let me find the right equation for orbital period. It's like you have to convert this to this AU,
Mm-hmm.
and that's what I see you doing here.
Yeah.
Okay, so let me back up to this. So this formula is right, but the number we used is wrong. So
Okay.
we have to start with the number, the 6.58 times 10 to the 11th meters, just like you did. And the AU, 1 AU, I guess we should figure out, did your instructor not give you like 1 AU in metric?
All that's on my equation sheet is 1 AU equals 93 million miles.
Okay. So then you do have to convert it to US. So like you did here, you said, okay, there's 1,000 meters in 1 kilometer. I think you did it the other way, but and then 1 kilometer, or I'm sorry, 1.6 kilometers is 1 mile, 1.61 mile, and then 93 times 10 to the 6th miles is 1 AU.
Mm-hmm.
Okay, and you got to get this number here. So you got to go to your calculator and do this horrible thing here. This lots of calculations here. Divided by 1,000. And anything you put in the denominator, just as a reminder, you want to put it in parentheses, just to be like especially this multiplication here. Yes. Okay, so this actually works out to being a reasonable number. It's 43.95 AUs.
Okay.
So the orbital period, the period is still a to the 3/2, but we can now use this number in this equation. So period is 43.95 to the 3/2 power. So period is 292 or 291-ish, right in there. Our AU number is very different. They must have Must have had something in the calculator go wrong on your side when you did it the first time.
Yeah, probably.
Oh, you know what? I got the wrong number here too. 93. Okay, so this isn't even right. It's 4 point. I'm sorry, 4.39. This number's not even right either. Oh boy. Yeah, so I got 9.2.
Okay.
I think that's, and that's good because the next question is going backwards. So we gotta be able to go forwards and backwards. We gotta be able to, you know, undo what we just did. So question 3. So question 3 is calculate the distance between a planet and the sun if the planet has an orbital period of 6.47 Earth years. So they're giving you P this time. They're saying P is 6.47. Okay.
Mm-hmm.
Okay, so that we're using the same formula, P squared equals A cubed. So this time though, we're solving for A. So you take the 1/3 power on each side. So A equals P to the 2/3.
Okay.
So this time, so A is going to equal 6.47 to the 2/3 power. So let's get that number. Grab your calculator. I'll do it as well. 6.47 to the 2/3 power. And I get 3.47.
Yeah.
So this is 3.47 AU. And now we have to go back convert it. So we know that 1 AU is 93 times 10 to the 6th miles. We probably want it in kilometers. So we know that 1 mile is 1.61 kilometers. And like, I guess we need to go to meters. So in 1 kilometer, there are 1,000 meters. This feels more like a unit conversion problem than anything, but. So I get 5.2 times 10 to the 11th meters.
Okay.
Okay, so can we go to the law of universal gravitation now?
Yes.
Okay. Okay, so this looks and feels like a lot of the questions we're doing, I think last time we met. The gravitational force between two objects is G M1 M2 over R squared. Do you recall that from last time?
Yes.
Okay, so this first thing, they've got a bowling ball and there's another ball. They're 2 meters away. One weighs 6.5 kilograms, the other we don't know. And we're given the force in newtons between them. So there's two approaches here. You can either put the numbers in and then solve for the variable, or you can solve for the variable without the numbers. Which would you like to do? So either put the numbers in first or solve for the variable without the numbers.
Solve for the variable without the numbers.
Okay, so we're trying to get to M2, which means we need to undo the R squared. So we're gonna multiply both sides by R squared. We did do, I recall we did do it this way last time. So that's G M1, M2, and these are all multiplying each other. So you can divide by G M1, G M1. Those cancel. So your mass 2 is the only thing left, or your mass 2 is the, I wrote R here. I guess you're probably using D in your formula. It's the distance between them squared times the force of gravity, G, which is that universal constant, times M1. So this is now just putting the numbers in. So the distance between them is 2. The force between them is the 1.1 times 10 to the minus 11. G is, what is G? G. Do you know? It's a 9. I don't remember these numbers.
G is 6.67 times 10 to the negative 11th.
Thank you. And the mass of the first one is 6.5. So the only thing from here is just getting it into the calculator correctly. We actually have no real reason to know how big or small this actually is. Okay, divided by 6. Okay, so I get 0.101 kilograms.
Okay, that's what I got too.
Fantastic. All right, let's look at number 2. Maybe number 2 is similar. Number 2 is, oh, this is this whole sea level business that we talked about before. Okay. Okay, so an 80 kilogram astronaut weighs 1.125 newtons while standing at sea level on a planet with a mass of 2.11 times 10 to the 25th kilograms. Determine the radius of the planet. So person is standing on the surface, and we know that their weight is mass times gravity.
Okay.
So their weight is given as 1.125, and we know that their mass is 80, but we don't know G, so we can calculate G. But they give you those 3 numbers. They give you weight and they give you mass.
Okay.
So let's calculate that number. 1.125 divided by 80. So I get 14.06.
Mm-hmm.
Okay. And this is the part that I think was like maybe a little bit unclear from last time. FG is G M1 M2 over distance squared. Okay. And this FG is this value right here. These are the same.
Mm-hmm.
Do you remember that from last time? Kind of,
Force of
maybe.
gravity and gravity are the same.
Yes.
Okay.
So that really helps here because we're trying to solve for D. So let's solve for D in this equation. We're going to multiply both sides by D squared. So D squared FG equals G M1 M2. And then we're going to divide both sides by FG. And then we're going to, so D squared equals G M1 M2 over FG. Then you take a square root of both sides. So your distance is the square root of g, m1, m2 over fg. You know g is 6.67 times 10 to the minus 11. M1 is either your planet or your human here, or person. I don't know what it is. Just says an astronaut. Okay. So that's your mass. Your mass is 80. M2 is going to be the mass of the planet. So the mass of the planet is this 2.11 times 10 to the 25th. And the force of gravity, well, we need that, and we calculated that to be the value 14.06. Take the square root of all that. All right, so I got a number here for you. That number is 8.95 times 10 to the 7th. Because we used SI units in the whole calculation, you can just safely say, oh, that's in meters.
Okay.
All right, that's everything here. Was there other things you would like to cover tonight?
I don't think so. These are the biggest questions I had.
Okay. Did you get everything down from here? Is there anything you'd like to go back? I will send the notes out pretty quickly, but it's usually faster if you need. Did you need to get anything else down from this tonight?
No.
Okay. Well, thank you for scheduling, and I will see you next time.
Okay, thank you.
Have a great night. Bye now.
Bye.